The United States is currently sitting on a staggering 173 degrees of temperature contrast between Texas and Alaska, and that stored energy is about to discharge in a major severe weather outbreak starting Wednesday and peaking Friday, March 6th. We're talking tornadoes, large hail, damaging winds, 12+ states at risk. But Friday is just the opening act. The same pattern keeps recycling through the rest of March, and the two top forecast models can't agree on whether the back half of the month brings more severe weather or a dramatic winter reset with snow reaching Oklahoma. Either way, the atmosphere stays violent. Tonight, we cover this week's intense updated forecast, the engine driving all of it, and why Friday is only the beginning. If this pattern has you unsettled, subscribe to the Skylab so you do not miss what comes next as this thing develops. Drop a comment telling me where you are right now and whether this storm train is heading your way. And if you think people need to see this, share it, because the more eyes on this, the more people are actually prepared for what is coming. Now, let's get into it. 173 degrees, that is the number you need to understand before anything else I tell you today makes any sense at all. On March 1st, 2026, the temperature in Laredo, Texas hit 103 degrees Fahrenheit. On that same day, in Alaska, the temperature was -70. 173 degrees of separation on the same continent, at the same moment in time. And here is what most people don't realize when they hear a number like that gap is not just a weather statistic. It is stored energy. It is atmospheric potential, coiled and pressurized, the same way a stretched rubber band stores the force that will eventually send it snapping across the room. Except the room in this case is the entire central United States, and what gets launched is not a piece of rubber, it is a storm machine, and on Friday, March 6th, that rubber band lets go. The Storm Prediction Center doesn't issue 15% significant severe probability areas at day 6 range in early March. That's not me being dramatic, that's just not something that happens routinely. A day 6 outlook requires enough confidence, enough model agreement, enough atmospheric signal that forecasters are willing to put a number on something 6 days away when the atmosphere is still deciding what it wants to do. On March 1st, the Storm Prediction Center issued a day 4 through 8 outlook that contained 2 separate 15% areas, one for Wednesday, one for Friday, 2 of them, separated by days but connected by something much larger. And here is what made meteorologists genuinely pay attention. The models agreed. The GFS, the European, the ensemble means, they lined up on Friday's setup with an unusual degree of early consensus. When you work in atmospheric science, model agreement at that range is a little like 3 different eyewitnesses independently describing the same suspect. You start taking it seriously. What they were all seeing was this: a trough structure driving southwest mid-level flow across the plains, with a jet streak ejecting northeast in a classic severe weather configuration. The right entrance region of that jet creates divergence aloft, which pulls air upward, which destabilizes the atmosphere, which gives storms the vertical acceleration they need to go from ordinary to dangerous. Deep layer wind shear was forecast to be strong, the kind that tilts updrafts, keeps them organized, and spins them. Meanwhile, the Gulf of Mexico was open for business. Moisture return was already underway by March 1st, with dew points forecast to climb into the low to mid-60s across Oklahoma and Texas by Friday. Forecast high temperatures for Friday read like a summer afternoon. 80 degrees in Dallas, 70 in Kansas City, 83 in Nashville. That last one is 20 to 40 degrees above normal for early March. The ingredients were textbook. The kind of setup that goes into a meteorology classroom as an example of what you look for. But here is the tension that every forecaster was sitting with. Textbook ingredients are necessary but not sufficient. What separates a scattered supercell day from a corridor outbreak is the mesoscale detail, the small-scale atmospheric behavior that only resolves in the final 24 to 48 hours. 3 things remained unresolved as of early March. The strength of the capping inversion, which is the warm layer aloft that acts like a lid on a pressure cooker and controls whether storms explode all at once or struggle to develop. The exact position of the dry line, the boundary between Gulf moisture and continental dry air that acts as a trigger line, and the timing of low-level jet intensification after sunset, which is the nocturnal wind acceleration that can rapidly increase tornado potential after dark. Scattered supercells, or an organized corridor outbreak? That was the question nobody could answer yet. And somewhere in the margins of that same pattern, almost as a footnote to the tornado headlines, were the early signals of something else entirely: flooding. And behind that, the ghost of winter, not quite finished with us. But before we get to what Friday unleashes, we need to talk about Wednesday, because Wednesday is not the event. Wednesday is the signal that tells you everything about what comes next. Wednesday's severe weather risk sits over southeastern Oklahoma and north-central Texas, and on its own it looks like a moderate early-season event. Instability is decent, shear is organized, and for early March on the southern plains that is already noteworthy. Early-season severe weather climatology on the plains does not look like May. The soil is not yet as primed, the Gulf moisture is not as deep, the surface temperatures are not as explosive. A Wednesday event in early March would normally be a local story, but Wednesday is not a local story. Wednesday is a conditioning event, and the difference matters more than the headlines suggest. When storms fire on Wednesday along that boundary zone in southeastern Oklahoma and north-central Texas, they do not simply produce weather and disappear. They leave things behind. Outflow boundaries, the cold pool edges generated by storm downdrafts, remain draped across the region for hours, sometimes days. Those boundaries become preferred lifting zones. They become convergence lines where the next round of storms preferentially initiates. Soil moisture from Wednesday's rainfall changes the surface energy budget, altering how aggressively the boundary layer heats on Thursday and Friday. Differential heating zones emerge between rain-soaked soil and dry surrounding areas, and those zones generate their own localized wind shear and convergence. Wednesday storms, in other words, rewrite the mesoscale map that Friday storms will inherit. And then Thursday arrives. The Storm Prediction Center, in their extended outlooks, listed the Arc-La-Tex region, where Arkansas, Louisiana, and Texas converge, under a predictability too low classification for Thursday. That phrase sounds like uncertainty, and it is. But it is a specific kind of uncertainty that tells you something important about the pattern. Predictability collapses when the atmosphere is in a state of high sensitivity, when small timing differences in shortwave trough ejection, small variations in boundary position, small changes in how much the cap erodes, can produce dramatically different outcomes. You do not get that kind of sensitivity in quiet, benign patterns. You get it in loaded ones. What creates that loading is the split flow regime overhead. The upper level atmosphere is not moving in a single unified current, it has fractured into two branches, a northern stream moving polar air southward, and a southern stream ejecting shortwaves from the desert southwest toward the Gulf Coast. When you have two separate streams of energy running parallel courses across a continent, you get serial shortwave ejections. One trough fires east, then another loads up behind it, then another. The pattern doesn't reset to neutral between events. It recycles. Each shortwave that ejects eastward is replaced by another one queuing up in the Pacific. This is why Wednesday and Thursday and Friday are not three separate weather stories. They are three pulses in the same heartbeat, and each pulse conditions the environment for the next one. Outflow boundaries from Wednesday storms enhance helicity, the atmospheric spin that feeds rotating updrafts in zones that Friday storms will track through. Wednesday's convection helps relax the cap that Thursday tries to erode. Thursday's chaos plants the boundary markers that Friday's dry line will interact with. The whole sequence is a setup within a setup within a setup. Think of it less like three weather events and more like priming a detonator, setting a fuse, and then watching Friday strike the match. Friday's setup is architecturally severe, and that phrase means something specific. It means the large-scale atmospheric structure, the bones of the pattern, are arranged in a configuration that generates dangerous weather, not by accident, but almost by design. The ejecting mid-level jet places its right entrance region squarely over the central plains during peak heating hours. That location matters because the right entrance region of a jet streak is where upper-level divergence is maximized, where the atmosphere is most aggressively pulling air upward and creating the suction that allows thunderstorm updrafts to accelerate vertically. Simultaneously, low-level flow from the Gulf of Mexico is being channeled northward through a moisture advection corridor, pumping warm, humid air into Texas, Oklahoma, Kansas, and Missouri in quantities that will reach the surface in the form of dew points in the low to mid-60s. That is summer-level moisture arriving in early March. The wind profile through the atmospheric column is veering, shifting direction from southerly at the surface to southwesterly and then westerly with altitude. Veering wind profiles are a tornado forecaster's setup requirement because they generate horizontal spin in the low levels that supercell updrafts can tilt into the vertical and then stretch into something with real angular momentum. Deep layer shear values are forecast to support supercell thunderstorms, the organized rotating storm structures that produce the most significant, severe weather. The warm sector is expanding northward of its climatological position for early March. Every structural element is in place. Now analog years, when meteorologists look back at early March setups with similar trough orientation, jet structure, and Gulf moisture return, they find some significant events in the historical record. The comparison is useful for calibrating expectations, not for predicting specific outcomes. No two setups are identical, and the mesoscale details that determine whether a day goes down as historic or merely active are never identical. But the analog suggests that when this pattern configuration has appeared in March in past years, the results have not been trivial. Storm mode on Friday is the critical variable that will determine the nature of the threat. Initially, the setup supports discrete supercells, individual rotating storms separated from each other, each capable of producing large hail, damaging winds, and tornadoes. Discrete supercells are the most tornado-efficient storm mode that exists. They are the architecture of the significant tornado events in the historical record. But as the evening progresses, the risk of mode transition increases. Linear convection, a quasi-linear convective system, a QLCS, can consolidate from individual cells and race eastward, trading tornado potential for widespread damaging winds and, critically, adding to rainfall totals. The tornado risk variables on Friday come down to three interacting factors. First, dryline position. If the dryline surges too far east too quickly, storms may initiate ahead of the prime shear environment and become outflow dominant before the best dynamics arrive. If it holds back, storms fire into a more favorable zone. Second, cap erosion timing. If the cap breaks too early, storms may form during hours when moisture return is incomplete. If it holds until afternoon, storms fire into a more loaded environment. Third, and most dangerous, the low-level jet ramp-up after sunset. The nocturnal low-level jet, the rapid acceleration of southerly winds in the lowest mile of the atmosphere that occurs after dark, can dramatically increase low-level wind shear and helicity after 8 or 9 p.m., injecting new rotational potential into storms that may already be ongoing. Nocturnal tornadoes have a higher fatality rate than daytime tornadoes because they occur when people are asleep, storm spotting networks are less active, and visual confirmation of tornado structure is impossible. If Friday's LLJ ramps aggressively after dark, the overnight hours become the most dangerous window. The cities in the corridor read like a roll call of the Southern Plains and Mid-South: Dallas-Fort Worth, Oklahoma City, Tulsa, Springfield, Kansas City. The Storm Prediction Center's 15% area covers Texas, Oklahoma, Kansas, and Missouri. That is a geographic swath that contains millions of people, and the 15% significant severe probability label means forecasters believe there is a meaningful chance this event produces tornadoes, hail, and winds that cause significant damage and injury. Here is what 15% doesn't mean. It does not mean outbreak is guaranteed. Atmospheric setups of this quality have fired into spectacular events, and they have also underperformed when mesoscale details resolved in ways that limited storm coverage or disrupted storm mode. The setup creates the possibility. The mesoscale execution determines the reality. What we know on March 1st is that the environment on Friday will be dangerous. What we do not yet know is how efficiently the storms exploit it. But here is the thing that nobody is talking about loudly enough in the tornado conversation. Tornadoes may not be the most destructive cumulative threat this week. Not by total damage cost, not by total impact area. Something else is loading quietly in the margins of this same pattern, and it does not announce itself with rotating wall clouds or tornado sirens. It just rains, and rains, and rains. 4 to 8 inches of rainfall in 7 days near Fort Smith, Arkansas. That is the number embedded in the Weather Prediction Center guidance for this outbreak period, and it sits in the forecast in a way that does not generate the same alarm as tornado watches, but should. Flash flooding is statistically the deadliest weather hazard in the United States on an annual basis. More fatalities per year than tornadoes, more than lightning, more than straight-line winds. People drive into flooded roadways, they are swept from low-lying areas without warning. The damage to infrastructure, roads, bridges, basements, water treatment systems, compounds across days in a way that single-event severe weather does not. And the pattern setting up this week is not designed to produce flooding as a side effect. The atmospheric configuration almost ensures it. Here is the mechanism. The same stalled and quasi-stationary boundaries that Wednesday's storms leave draped across the Mid-South become training lines for subsequent convection. Thunderstorm training occurs when multiple storms form sequentially and track along nearly the same path, each one dropping rainfall over ground that is already wet from the previous storm. It is the meteorological equivalent of repeatedly filling the same bucket. The Weather Prediction Center identified excessive rainfall marginal zones in their Day 4 and 5 outlooks that are elongated along a corridor from Dallas northeast through St. Louis and into the Ohio Valley. That elongation is the signature of a training pattern. It tells you the boundary is not moving, the storms are staying on the same track, and the rain is going to stack. 4 to 8 inches over 7 days in one location sounds manageable until you consider that the Arkansas River Basin, the Red River Basin, and the tributaries feeding into the Mississippi system are already carrying winter's legacy in their soil moisture profiles. The January 23rd through 27th winter storm placed 230 million people under weather alerts, one of the largest single-event impact footprints in recent memory. That storm deposited snowpack across a massive region, some of which is now melting into soil that is already saturated. When rain falls on saturated soil, it doesn't percolate. It runs off immediately, and it does so at a rate that overwhelms drainage systems designed for normal conditions. There is also a resource fatigue dimension to this that the weather community does not always foreground. FEMA pre-positioned supplies before the January storm. National Guard units were activated across multiple states. Emergency management agencies worked extended deployments to handle the winter impact, and many of those same systems are now being asked to pivot immediately to flash flood watches and potential tornado emergency protocols. The human infrastructure of disaster response, the people, the equipment, the organizational attention, has a capacity limit, and back-to-back major weather events stress that capacity in ways that individual events do not. The compound hazard threat on Friday may be the most underappreciated element of the whole setup. The same counties in eastern Oklahoma, western Arkansas, and southwestern Missouri that face tornado risk in the afternoon and evening also face flash flood risk overnight as QLCS lines race through dropping additional rainfall on already inundated ground. A county can simultaneously be under a tornado warning and a flash flood warning. The choice between sheltering in place for a tornado in a low-lying structure versus evacuating for flooding is not a clean one, and emergency managers dread exactly this scenario. The central argument of everything we have covered so far is this. Friday is not an isolated spike of severe weather followed by a return to calm. Friday is the first visible discharge of a pattern that is not finished. The atmosphere loaded itself with 173 degrees of temperature gradient, set the machinery in motion across 3 consecutive active days, and is preparing to release that energy in a multi-hazard corridor event. And the machinery, as it turns out, does not switch off after Friday. It is designed to reload. The real question is not how bad Friday gets. The real question is what happens to a country in the weeks after Friday, when the same pattern that built this event refuses to collapse, and the 2 most sophisticated forecast models on the planet cannot agree on what comes next. To understand why this pattern keeps recycling instead of resolving, you have to understand the engine that is running it, and that engine is the temperature gradient itself. A meridional temperature gradient is the difference in temperature between the equator and the poles, expressed as a rate of change per unit of distance. When that gradient is steep, when the temperature drops dramatically over a short distance, the atmosphere converts that temperature contrast into wind, specifically into the jet stream. The steeper the gradient, the faster and more energetic the jet stream. And when the jet stream is fast and energetic, it does not flow in gentle, nearly straight curves from west to east. It amplifies, it develops large north-south waves. It digs south in some places and surges north in others, creating the conditions for extreme weather on both sides of the boundary. In late February and early March 2026, the polar air is not retreating, it is pooling. A reservoir of Arctic air is anchored over northern Canada and Alaska, reinforced by persistent high pressure, and it is not moving poleward and dissipating the way it would in a normal late winter pattern. At the same time, the subtropical ridge, the belt of high pressure that normally sits well to the south, is expanding aggressively northward over the southern tier of the United States. Tropical and subtropical air is being drawn much farther north than March climatology suggests it should be. These two air masses, the stubbornly cold north and the aggressively warm south, are meeting over the central United States, and they are meeting over a narrow zone. That narrow zone is the baroclinic zone, the atmospheric boundary where the temperature contrast is most extreme, and it is the baroclinic zone that is anchoring the severe weather corridor this week. The jet stream is not meandering leisurely through a broad transition region. It is racing along the top edge of a cliff face where temperatures change by dozens of degrees over distances of a few hundred miles. The energy conversion that happens inside a baroclinic zone is what drives everything we have discussed. The temperature contrast creates a pressure gradient. The pressure gradient accelerates wind. The wind creates shear, differences in wind speed and direction with height. Wind shear combined with atmospheric instability is the raw material of severe thunderstorms. The 173-degree spread between Laredo and Alaska is not just a dramatic statistic. It is the fuel source. It is the reason the models agreed on Friday. It is the reason Wednesday and Thursday are active. It is the reason the pattern does not simply exhaust itself after one outbreak and reset to quiet. The rapid seasonal transition overlap zone is the other piece of this. Early March sits at the intersection of two opposing seasonal air mass regimes. Winter still has a grip on the polar regions. Spring is rapidly advancing from the south. When those two regimes clash during a period of high jet stream amplitude, you do not get a gradual handoff. You get a violent negotiation, conducted in the language of supercells and blizzards and flooding rains, all happening simultaneously across different latitudes of the same continent. This is why Friday's outbreak is not a standalone event. It is the first visible discharge of the gradient engine, and as long as that gradient, 173 degrees of stored atmospheric potential, remains locked in place, the engine keeps running. The question is what it produces on the next cycle. And the answer to that depends on something called split flow, and it is more alarming than it sounds. The Weather Prediction Center used a specific phrase in their extended forecast discussions around this period, pronounced split upper flow pattern. That phrase is technical, but its implications are not subtle. The upper-level atmosphere over North America has fractured into two separate flow regimes, running roughly parallel to each other. The northern stream is carrying Arctic air reinforcements southward across Canada and into the northern United States. The southern stream is channeling Pacific energy eastward along a more subtropical path, ejecting shortwave troughs from the desert southwest and northern Mexico into the Gulf Coast and southern plains. When these two streams are operating simultaneously, you get a conveyor belt effect. The southern stream loads a trough, fires it east, and another one queues up behind it in the Pacific. The northern stream keeps refreshing the cold air supply so that each successive trough has cold air available to interact with the Gulf moisture that the subtropical ridge is pumping northward. The whole system becomes self-sustaining in a way that a single stream pattern does not. Single stream patterns exhaust themselves. Split flow patterns recycle. The mechanism of recycling works like this. A southern stream trough digs into the desert southwest, gains energy from the temperature contrast along the baroclinic zone, ejects northeast, triggers the severe weather event, and then loses its identity as it merges with the larger circulation. But while that is happening, another shortwave is already rounding the ridge in the eastern Pacific, ready to follow the same track within days. The first ejection is Friday, March 6th. What the models were hinting at around March 10th and 11th is the next ejection, and that one has a different character. The March 10th through 11th potential involves a deep, low-pressure system tracking into or near Iowa. Deep lows in that position create the classic dual threat setup that meteorologists dread in early spring, because the circulation of a deep low simultaneously draws warm Gulf moisture into its southeast quadrant, while pulling Arctic air southward into its northwest quadrant. In the northwest quadrant, you get blizzard conditions, heavy snow, high winds, rapid temperature drops. In the southeast quadrant, you get the moisture and instability for severe thunderstorms and tornadoes. The same storm, two completely different faces, separated by a matter of 200 or 300 miles. The Central Rockies would face significant heavy snow potential. The Sierra Nevada is already running below average for snowfall this season, a distribution imbalance that reflects the same amplified pattern that is concentrating precipitation events in the central and eastern portions of the country, rather than distributing moisture more broadly. The western drought story and the central flooding story are two manifestations of the same atmospheric pattern. Now consider what this means in the context of Friday being the first ejection. If the split-flow conveyor belt keeps loading and firing shortwaves every 5 to 7 days through mid-March, the severe weather community is not looking at a one-week active period. It is looking at a prolonged surge that could stretch through the heart of a month that has historically been underestimated as a severe weather threat. Friday ignites the sequence. But the sequence does not end with Friday. And just as this pattern begins to intensify, something changed in the way we even talk about the risk. Something that the Storm Prediction Center did on March 3rd altered the language of severe weather communication in a way that has not happened in decades. On March 3, 2026, the Storm Prediction Center launched something called Conditional Intensity Groups, or CIG. This is not a minor procedural update. It is a fundamental restructuring of how significant severe weather risk is communicated to the public and to emergency managers. The old system used a 10% hatched area to indicate significant severe weather potential, that crosshatch zone on the Outlook maps that indicated where the most intense events were expected. The problem with that system was binary. You were either in the hatched area or you were not. There was no way to communicate gradations of intensity risk, no way to indicate that some locations faced a higher probability of the most dangerous outcomes than others within the same hatched zone. Conditional intensity groups replaced that system with tiered intensity communication. Instead of a single hatched area, forecasters can now communicate multiple risk tiers, each corresponding to different probabilities of the most intense events, significant tornadoes, very large hail, extremely damaging winds. The public for the first time gets a richer picture of not just where severe weather is possible, but how dangerous the severe weather that does occur is likely to be. The timing of this launch is striking. The first real-world test of the conditional intensity group system may occur during this very outbreak. A significant severe weather event in the first week of the new system's existence means the forecasting community, emergency managers, and the public will be encountering this new communication framework under live, high-stakes conditions. The way people understand and respond to Friday's risk maps may look measurably different from any previous event. Even the language of the warning is evolving at the exact moment the storm machine begins its first cycle. Around March 13th, the two most sophisticated deterministic weather forecast models on the planet are depicting two different versions of the United States. The European model, the ECMWF, widely regarded as the most accurate global forecast model for medium-range prediction, shows temperatures running 10 to 30 degrees below normal across the central and eastern United States. It shows the possibility of snow pushing into Kansas, Oklahoma, and potentially northern Texas. It shows a late winter reset of significant magnitude arriving in the second week of March, driven by a deep trough digging into the central continent and pulling genuine Arctic air southward. The American GFS, the global forecast system, shows the opposite. A southeastern ridge dominates, temperatures run above normal. The cooldown in the GFS solution is modest, 5 to 7 degrees below normal at most, and brief, no significant winter intrusion. The severe weather pattern does not give way to a winter reset. It continues, fed by persistent warmth in the southern tier and ongoing Gulf moisture return. These are not marginally different solutions. They are atmospherically opposite. One model is showing winter's last gasp as a dramatic, potentially significant event. The other model is showing it as barely a hiccup in what is otherwise an accelerating spring severe season. Both cannot be correct, and at day 10 and beyond, neither one should be treated as a forecast. This point bears emphasis because it is one that the public often misunderstands about extended range modelling. A deterministic model run at 10 to 14 days is not a forecast. It is a scenario, a single solution drawn from a model that is exquisitely sensitive to initial conditions that are themselves imperfectly observed. The atmosphere is a chaotic system. Small errors in how we measure wind speeds, temperatures, and moisture at any given moment cascade forward in time, compounding exponentially. By day 12, those initial condition errors have had enough time to grow into completely different atmospheric states. What makes the GFS Eurodivergence significant is not that they disagree. They always disagree at long range. What makes it significant is the magnitude of their disagreement and the nature of it. They are not showing two versions of the same storm with different intensities. They are showing two completely different circulation patterns. The ensemble spread, the spread of solutions from dozens of individual model runs initialized with slightly different starting conditions, is widening rapidly beyond day 8. That widening spread is the atmosphere's way of telling you that the pattern is unstable, that it is highly sensitive to upstream conditions in the Pacific that we have not yet fully observed. The two upstream drivers that determine which model verifies are the timing and amplitude of Pacific jet energy injection into the western United States, which controls how aggressively the next trough digs southward, and the strength and southern extent of the Arctic air reservoir over Canada, which determines whether the trough has cold air available to pull into the lower 48 when it digs. Neither of these things is pinned down with confidence at day 10. What both models agree on is that the central United States remains active. Neither solution produces a quiet, dormant second half of March. The disagreement is about the character of the activity, severe thunderstorms or blizzard conditions, or some combination of both cycling through in alternating bouts. Either way, calm is not on the menu. What happens beyond Friday lives inside a volatile, unstable atmospheric regime where even the most sophisticated tools we have built to read the future are giving us fundamentally different answers. The reason the GFS and the European model are showing such dramatically different solutions for the second week of March comes down to a concept that sounds abstract, but has very concrete consequences: sensitive dependence on initial conditions, or what most people call chaos theory. Edward Lorenz, the meteorologist and mathematician who formalized our understanding of atmospheric chaos, demonstrated in the 1960s that mid-latitude weather systems are fundamentally chaotic. Not random, chaotic. There is a difference. A random system has no memory and no structure. A chaotic system has both, but its evolution is exquisitely sensitive to starting conditions in a way that makes long-range deterministic prediction theoretically impossible beyond a finite horizon. For weather, that horizon is generally estimated at 2 to 3 weeks for large-scale pattern features. The current pattern is operating near the upper end of its sensitivity. A high-amplitude jet stream, one with large north-south waves, is more chaotic than a relatively flat zonal jet. Large waves amplify and propagate in ways that are harder to predict than smaller waves. The timing of wave breaking, the point at which a ridge collapses and a trough digs, can shift by 24 to 48 hours based on upstream disturbances that are barely within our current observational network. And a 24-hour timing shift in a pattern like this does not produce a 24-hour forecast error. It produces a pattern that looks completely different at day 12. The Pacific jet is the wild card. Energy crossing the Pacific in the 5 to 10-day range is observed incompletely. We have satellites, aircraft reconnaissance, and a surface observing network. But the Pacific is enormous and our coverage is finite. Small wave packets that will eventually phase with the downstream trough can arrive slightly earlier or slightly later than models project, and that slight difference, fed forward through the chaotic atmosphere for 10 to 12 days, produces a Euro solution and a GFS solution that barely resemble each other. The Arctic air pool over Canada adds another layer of volatility. Arctic air reservoirs are not monolithic. They have internal structure, weaker and stronger lobes, boundaries between different air mass densities that models may handle imperfectly. Whether the March 10th through 11th system taps deeply into the coldest available Arctic air or clips the southern edge of a shallower reservoir determines whether you get a historic blizzard in Kansas or a cold rain event. Models are sensitive to exactly this distinction at long range, and they are currently not converging. Historical examples of similar model divergence resolving dramatically are not difficult to find. In numerous cases over the past decade, extended range disagreements of this magnitude have verified on the extreme end, meaning the atmosphere chose one of the more dramatic solutions when it finally declared itself. This does not mean it will do so now. It means the uncertainty is real, the disagreement is meaningful, and the range of possible outcomes for the second half of March is genuinely wide. Friday is the known event. Everything after it lives inside a pattern that is still negotiating its own future. And that negotiation may determine whether March 2026 becomes a landmark month in the severe weather record. 2024 was the second most active tornado year on record. The Storm Prediction Center documented that final tally with the kind of quiet understatement that professional forecasters use when a number is large enough to speak for itself. Second most on record. And now, in 2026, the severe weather signal is arriving early, with unusual intensity, in a month that the public does not historically associate with outbreak-level events. March has always had its severe weather moments. The super outbreak of 1974 began in early April, but its predecessor events in March of that year were already signaling an overactive spring. The March 2012 outbreak sequence produced significant tornadoes across the Midwest before most people had mentally transitioned from winter to spring. But the general public perception of severe season, the instinctive image of tornado alley activity, still defaults to April through June. March tends to catch people off guard. What is different about this year's early March signal is not just the magnitude of Friday's setup. It is the early warmth expanding north of its climatological position, the Gulf moisture return occurring ahead of schedule, and the rapid seasonal overlap zone arriving weeks before it typically does. The warm sector on Friday is pushing into latitudes where, in most years, below normal temperatures would suppress convective development. The atmosphere is not reading the calendar. There is a cautious way to frame what this might mean, and it is important to apply that caution rather than reaching for a sweeping conclusion. Short-term pattern behavior is not long-term trend attribution. A single active March, even an exceptional one, does not by itself tell us something definitive about climate trajectories. Attribution science is complex, layered, and requires much longer data records and more rigorous methods than observing one month's weather. What we can say practically is this: the volatility window for significant severe weather appears to be extending earlier into the year based on recent observations across multiple seasons. Whether that represents a robust shift or natural variability operating at its extreme end is a question that requires more than one data point to answer. What we can observe right now, in practical terms, is that the cumulative fatigue from the winter storm season is colliding head-on with the beginning of severe weather season. The population that endured the January blizzard sequence, the northeast snowfall events with totals reaching 30 to 37 inches in some areas, the National Guard activations and FEMA supply pre-positioning, that same population is now being asked to pivot their emergency awareness and preparedness posture to tornadoes, large hail, and flash flooding within weeks. Emergency managers describe this transition as one of the most challenging aspects of the winter to spring handoff in an active year. The public attention cycle, the media alert cycle, and the emergency resource cycle all have momentum. Rapid pivots are cognitively and logistically demanding. If March 2026 does represent an inflection point, the beginning of an earlier, more sustained severe season rather than a brief anomalous spike, then the weeks after Friday will reveal that. And the answer to whether this is a surge or a spike depends entirely on whether the pattern that loaded Friday keeps reloading. Which brings us to the only mystery that matters now. In the short term, the mystery is simple to state and impossible to answer from here. How bad does Friday get? The atmospheric architecture is dangerous. The ingredients are aligned. The structural setup supports supercell thunderstorms, significant tornadoes, very large hail, and damaging straight-line winds across a corridor that covers Texas, Oklahoma, Kansas, and Missouri. The Storm Prediction Center has already committed a 15% significant severe probability to a Day 6 outlook, a commitment they do not make casually. The moisture is there, the shear is there, the forcing is there, but storm mode is undetermined. The difference between a day of discrete supercells tracking in relative isolation through the warm sector and a day where those supercells consolidate into a QLCS by early evening is measured in thousands of square miles of impact area and in the nature of the dominant hazard. Discrete supercells maximize tornado potential. A QLCS maximizes damaging wind and rainfall efficiency. The setup supports either transition and the mesoscale details, dryline position at initiation, cap erosion timing. Exactly when and how aggressively the low-level jet ramps up after dark will not be resolvable until we are within 24 to 48 hours of the event. The nocturnal window is the piece that keeps experienced meteorologists awake. If Friday's storms remain ongoing after sunset and the low-level jet intensifies as forecast in the 12 to 18 hours after midnight, the overnight hours from Friday into Saturday morning carry their own tornado threat, one that arrives when warning lead times matter most and when the people in the path of those storms are least likely to be awake and monitoring. And then there is the larger mystery, the one that extends beyond Friday and out across the rest of March in two contradictory directions. The 173-degree gradient is still loaded. The polar air is still pooling. The subtropical ridge is still expanding. The split flow pattern is still cycling. The conveyor belt that produced Wednesday, Thursday and Friday is not scheduled to shut down after Friday. The next shortwave is already forming in the Pacific. The March 10th through 11th system is already showing up in model guidance as a potential dual-threat low that brings blizzard conditions to the northwest quadrant and tornado risk to the southeast quadrant simultaneously. And beyond that, around day 12 and 13, the models diverge into their two incompatible versions of the United States. The European model's dramatic winter reset, with temperatures 10 to 30 degrees below normal and snow reaching Kansas and Oklahoma, versus the GFS's continued warm pattern with only modest cooling and a severe weather season that accelerates rather than pauses. Both of those futures are plausible. Both are consistent with the upstream conditions as they exist right now. The atmosphere has not yet decided which one it is going to execute. What we know is that neither one produces calm. Neither one produces a quiet second half of March in the central United States. The disagreement between the models is not about whether the pattern remains active, it is about whether the activity takes the form of supercells or blizzards, of tornado watches or winter storm emergencies, of flooding rains or snow-covered plains. The answer to that question, the resolution of the model war, is going to unfold in real time over the next 2 weeks, and it is going to be visible in the forecast maps, in the storm reports, in the emergency declarations, and the damage surveys. The atmosphere is going to tell us which future it chose, one model update at a time. Here is what we know with certainty as of this moment. The rubber band is released. Friday is the first snap. The 173 degrees of stored potential that spent weeks coiling across the continental temperature gradient has found its path to discharge, and the discharge has begun. The question is not whether the energy is real. It is. The question is not whether the pattern is dangerous. It is. The question is how the atmosphere chooses to spend what it has stored and over how many weeks it decides to spend it. We are standing at the beginning of a sequence that could define March 2026 as a landmark month in the weather record, or it could pivot dramatically toward winter's last stand and redraw the map entirely. The storm machine is running, the conveyor belt is loaded, and somewhere in the chaos of the Pacific jet and the Arctic air reservoir and the split flow pattern still cycling overhead, the atmosphere already knows exactly what it is going to do. It just has not told us yet.